Are we in simulation?
Every choice has a cost. Let's find out. Space-Time Cafe.
All right, welcome. Today, we are tackling one of the biggest questions you can possibly ask, but we're coming at it with a really fascinating scientific angle. We're going to unpack a framework that basically acts as a reality detector. Yeah, you heard that right. A measurable way to test if our world is the real deal, or if it's just a stunningly advanced simulation. So, here it is. The big one. Are we living in a simulation? You know, it's the kind of question that fuels those late-night conversations. It's the premise of so many incredible sci-fi movies. Are we all just, avatars in some kind of cosmic video game? It's a seriously mind-bending idea. But we're going to move past just the philosophical side of things. I mean, what if you could actually turn this thought experiment into a proper scientific investigation? What if there were real, tangible clues we could search for? Like we're detectives on the ultimate case, the case for reality itself. This, right here, gets to the absolute heart of it. In a simulation, like any video game you've ever played, you can always hit reload. You can just go back to your last save. But in reality, choices have consequences. They're irreversible. You spill your coffee? Well, you can't just undo that for free. It takes energy. It takes work to clean it up. Reality, it turns out, always comes with a bill. So to really understand this cost, this bill, let's dive into our central mystery. And we're going to frame it as the Lego castle problem. Trust me, this simple analogy, it's the key that unlocks this whole detector. Okay, so just picture this. You and a couple of friends, you're all set to build an epic Lego castle together. But here's the catch. Each of you has a slightly different picture of what the final castle is supposed to look like. Your friend's blueprint has a giant moat, but your plan has awesome laser turrets on the walls. How on earth do you build one single castle together? This little scenario gives us all the key terms we're going to need. Those different blueprints, we're going to call those incompatible local charts, basically just different local views of the truth. Now, to handle this mess, you'd probably have to split into teams, right? That's called partitioning the problem. And all that effort, the arguments, and the rebuilding you have to do where your designs clash, that's the real irreversible work you have to put in. And this, right here, this is our first huge clue. I mean, think about it. If everyone's blueprint was exactly the same, you could all just work together as one big happy team. That's a partition of 1. We call that R equals 1. That's what a simulation looks like. But if your blueprints are so different that you must split up to avoid, building a contradictory mess, then your R is greater than 1. And that is the signature of reality. So, okay, Legos are one thing. But how does this whole price of disagreement pop up anywhere else? Well, it turns out this isn't just for toys. It's a universal principle. And once you know what you're looking for, you start to see it absolutely everywhere. Just take a look. In software, when you merge a public commit that other people are already using, well, you can't just undo that without creating total chaos. Our detector calls that real. Or cooking. Ever tried to uncook a steak? That beautiful browning, the Maillard reaction, is completely irreversible. That's real. And in the legal world, once a plea or a judgment goes on the public record, it sets off a chain of events you can never perfectly rewind. The detector flags all of these as real. Okay, so we've established that reality has a cost. But how does the universe actually enforce this? I mean, what's the mechanism? This leads us straight to the smoking gun in our investigation, a fundamental law of physics that we can think of as the universe's deletion field. It's officially called Landauer's principle, and it is a massive deal in the physics of information. What it says is that anytime you erase a piece of information, I mean truly permanently delete it from existence, you have to pay a physical price. And that price is a minimum amount of energy that gets released as heat. And here's the actual bill. Now, it's a super tiny number per bit of information, but here's the critical part. It is not zero. It's the universe's non-refundable thermodynamic charge for making something forgettable. In a simulation, a computer could always just keep a backup somewhere. But in reality, to permanently delete something, this energy must be paid. So here's the crucial link. This brings us right back to our Lego castle. When you and your friends finally have to agree on one design, the one with the moat or the one with the lasers, and you discard the other possibilities, you are literally erasing information. That act of choosing, of committing, that's what you're paying the Landauer bill for. But hang on. Why? Why are we forced to make these costly choices to begin with? What's the motive behind this cosmic rule? Well, it all boils down to something you can think of as the impossible map. We're forced to choose because our local views sometimes have a fundamental twist in them. Think about trying to flatten a globe of the Earth onto a single sheet of paper. You just can't do it perfectly, right? You always get weird distortions at the poles. The Earth has a curvature, a twist, that makes a perfect flat map impossible. Well, the universe is kind of like that. Our local charts sometimes have these twists that prevent them from being stitched together into one single, globally perfect picture. So how does a twist like this even form? Well, it happens step by step. First, you've got your local maps, and each one is perfectly fine on its own. Then you try to glue them together where they overlap. But then, you discover a mismatch. You find that if you trace a path through several of your maps, you don't end up back where you started. That contradiction forces you to make a cut, to make a split, to keep the whole thing from falling apart. And get this whole twist idea isn't just some convenient metaphor we're using. No way. It is a real, measurable mathematical object. For the math nerds out there, it's called a bundle gerb, and you can even measure its size. The point is, this whole framework is built on a super solid, rigorous mathematical foundation. This is not just a bunch of hand-waving.
Okay, we have gathered all the clues. We have the price of disagreement, we have the physical law that acts as the enforcer, and now we have the topological reason it's all necessary in the first place. So it's time. Let's put it all together and finally run our reality detector.
The entire logic, the whole detective story, can be boiled down to this one simple and incredibly powerful chain of events. A fundamental twist in the information forces you to create splits, or partitions. And creating those splits requires an irreversible physical cost. Twist leads to splits, leads to cost. Simple as that.
And here it is, the central law of our detector, written out as an equation. It's really just a formal way of saying what we've discovered. If the minimum number of partitions you need, that's our R epsilon, is greater than 1, then there must be a minimum amount of work or energy cost that is greater than 0. No way around it.
Now that key variable, R epsilon, has a proper name. It's called the paving number. And this isn't some hypothetical idea we just came up with. Its existence is mathematically guaranteed by the solution to a really famous, really hard math problem called the Singer problem, which was only solved back in 2015. So this gives our detector a rock-solid, proven foundation.
So the final test is actually beautiful in its simplicity. You just measure the paving number of a system. If that number is 1, it means all the different viewpoints can secretly be reconciled into a single picture. It can be a simulation. But if that number is greater than 1, it means the system has these irreducible twists. It has to be split. It's real. And what's so amazing about all this is how it brings everything back to our own lives. You know that feeling of friction? The difficulty of making a hard choice? The real cost of committing to one path over another? That's not a bug in the system. That's not a flaw. That is the very signature of living in a real universe. Which leaves us with this final, really provocative thought to sit with. A simulation can always be rewound. It can be restored. Its past can be perfectly remembered without any cost. But reality forces us to pay a thermodynamic price to move forward, to make choices, and to forget what might have been. So maybe that's the best definition we have.
Reality is what you cannot perfectly forget.